Welcome to Today I Learned Climate, the show where you learn about climate change from real climate scientists. Today's question is, what are those white lines that trail behind airplanes, and what do they have to do with climate change? To get more insight around today's question, I reached out to Professor Steven Barrett, who leads MIT's Laboratory for Aviation and the Environment.
My name is Steven Barrett, and I've been at MIT for 8 years now, trying to improve the scientific understanding of how aviation impacts the environment, with a particular focus on climate change and air pollution.
You may have read some headlines about why flying has become enemy number one for many climate change activists. An article from the Washington Post from November last year is literally titled, "For the Love of Earth, Stop Traveling." I don't know about you, but I love to travel. But I hate the fact that something that I love to do creates so much pollution.
I mean, a lot of people view environmental constraints as sort of an existential threat to aviation. And I believe at least aviation is positive, and the more people who can explore the world and experience different cultures and take up educational and work opportunities and see family and friends, the better.
So Professor Barrett and his research team are not only working to better understand the problems of aviation and climate change, but are also developing solutions.
Like electric aircraft and also biofuels and other policy changes.
So we'll talk about those later. But first, let's break down the problem. Planes burn jet fuel, and when they do, they release two gases. The most important are carbon dioxide and water vapor, water in its gas form. You're probably familiar with the climate impacts of CO2. This gas gathers in the atmosphere and forms a kind of blanket around the Earth, trapping in heat and bumping up the average temperature of the planet. For hundreds of thousands of years, this has created a very comfy place for humans and life to live. But as we've been adding more and more CO2 to the atmosphere, the blanket is becoming thicker and thicker, warming the planet more than we have in millennia. So just as a side note, I highly recommend checking out the climate primer that we've posted on our new MIT climate portal, climate.mit.edu. You'll find a link to this in our show notes. Okay, so the CO2 is creating this thick blanket, making us warmer. The main issue with CO2 is that it sticks around in the atmosphere for a long time.
CO2 has a lifetime in the atmosphere of hundreds of years. Now, most of the CO2 that aviation has ever emitted is still in the atmosphere because it lasts so long.
Think about fighter planes circling Europe in World War I, or Charles Lindbergh flying across the Atlantic Ocean in 1927. The CO2 from those flights are still in the atmosphere.
And so we're now experiencing the warming from all that accumulated CO2.
Okay, so that's CO2, but planes also emit water vapor.
When aircraft fly through a sufficiently cold or wet part of the atmosphere, it leaves behind it an artificial cloud called a contrail,
which is short for a condensation trail, because the water vapor condenses into ice crystal in the cold air.
Which are kind of line-shaped artificial clouds you sometimes see behind aircraft. And they form within a few seconds, and they last a few hours if they form and persist.
Understanding how contrails interact with heat and sunlight is going to be really important in this episode, so let's break this down for a moment. So normally heat and sunlight enters our atmosphere and warms the Earth, as we all know. Some of that heat bounces back off the surface of the Earth and leaves the atmosphere. So contrails do two things inside of this process. They reflect incoming heat from the sun so that heat never reaches the Earth's surface. And they also absorb the Earth's heat, keeping in the heat that would normally never stay in our atmosphere. You could say that contrails act like both a jacket and a shade. They absorb heat radiating off of the Earth, like how a jacket keeps in your body heat. And at the same time, they also act like a shade, preventing sunlight that would have normally warmed the Earth from ever hitting the surface.
At nighttime, they're always warming because there's no incoming solar radiation, but there is outgoing infrared, which gets trapped. And then in the daytime, they can either be warming or cooling.
That's because it also matters where the contrail is. The balance of absorbing versus reflecting heat changes depending on if the contrail is over a darker area, like the ocean, which absorbs more heat than it reflects, or over brighter areas, like ice, which reflects more than it absorbs. If you want to know more about this, check out our show notes on climate.mit.edu. Overall, just like your jacket, scientists think that contrails have a warming effect, trapping in more heat than they reflect. And the models show that this warming effect is dramatic.
So you have as much warming from the last 6 hours of contrails as you do from the whole history of aviation CO2 emissions.
Whoa. So contrails contribute a lot to warming, but only temporarily, whereas CO2 lingers for hundreds of years. In fact, after 9/11, all planes were grounded for 3 days, and scientists studied and were able to see and measure how the lack of contrails really did impact the planet's temperature. Which brings up another question. How do scientists actually study this stuff?
Yeah, I mean, in some ways, a lot of climate science is difficult because we don't have a spare planet to do a controlled experiment on, and that makes life much harder. So if we could create one, that would be ideal. But failing our ability to do that, we've got to approach problems in a more piecewise way. So that means building up models from rigorously verified pieces of evidence. So sort of say, for example, creating models of atmospheric chemistry, verifying those models of atmospheric chemistry, including verifying that experimentally in say, smog chambers.
So Professor Barrett and his team build and use climate models to try to simulate what's happening 10 miles above us.
A model is a computer representation of equations that govern physics. So they're equations that are transformed into computer code, and these things usually have millions of lines because you're trying to model or trying to capture in a computer code what's going on from chemicals reacting to emissions into the atmosphere to clouds forming, winds, rain, a huge number of different processes that all get put into climate and atmospheric models.
Most computer models can take weeks, months, or even more than a year to run on supercomputers because they require so much computational power.
So you can run sort of hypothetical cases and use the answers to understand what the effect is of aviation either now or in the future, or if you were to change it some way. You have generations of researchers who contribute a piece to the work. And in this case, often they'll kind of work on, modify, improve, or create computer codes that represent or improve the representation of some kind of physics or chemistry process. And the models that get built that represent the atmosphere and how it responds are the product of hundreds of PhDs across scores of universities over decades. So this kind of atmospheric and climate models represent the sum total of generations of people's work towards building them.
Okay, so CO2 is still lingering and will still be lingering for hundreds of years. And contrails also trap heat depending on how many planes are flying at any given time. So how much does this actually matter? Well, if you include both the CO2 and contrails, aviation contributes about 6% of the warming we're experiencing today. 6% might sound small, but it's actually a really big number. The country of India contributes 6% of the world's greenhouse gases, and it's the world's third largest emitter. And aviation is on the rise.
The current forecasts are that aviation would double or triple by mid-century. And at the same time, most scientists say that you want to reduce CO2 emissions by about 80%. So even though today aviation is only about 6%, if we want to reach something like an 80% or more reduction in CO2 emissions while enabling growth in aviation because of the positive effects it has on society, that creates a huge challenge that is very difficult to answer.
These are hard questions, but many people around the world are working on solving them. Airline industries are always looking at more and more fuel-efficient planes, largely because it's in their economic interest to do so. Researchers like Professor Barrett are developing super-efficient plane technologies. Companies are manufacturing lower carbon fuels like biofuels made out of plant matter. There are a lot of solutions being pursued, and there are great challenges with each of these solutions. But one thing is for sure. Because of how long CO2 lasts in the atmosphere, the decisions that we make now have an impact far into the future. To see some of the work that MIT and others we know are doing to reduce aviation's impact on climate change and other cool climate science explanations, check out todayIlearnclimate.mit.edu. That's tilclimate.mit.edu. Thanks to Professor Barrett for coming in and speaking with us, and thank you for listening.